last morning of our last panel of economic policy in this form. Let me just, before we start, thanking again Giacomo and Emilio for the fantastic work that they put in organizing this panel and choosing these great papers. I really appreciate your effort. I know how much effort you put in this, and I think the result is just fantastic. And then also to thank again Despoina, which is here, because she's the one that organizes everything, and Mariolina, that again, as I said last time, she's economic policy, actually. So many thanks for all the great work that you always do for us. And so we can start. We have a very exciting morning today, and a long one. So if you need coffee, meanwhile, it's there. And the first presenter of the morning is Gino, and so the rules are like yesterday, 25 minutes plus time for Axelle for the discussion, and then the general discussion.
Okay, thank you so much. So first of all, I would like to thank the organizers for putting the paper in the program. I would also like to take the opportunity to thank the whole editorial team of economic policy. I've been a panelist myself, and I've enjoyed it a lot in the past. So I hope that economic policy will continue its great tradition. So here I'm going to present this paper, Artificial Intelligence and Jobs, Evidence from US Commuting Zone, and it's a joint work with Alessandra Bonfiglioli, Rosario Crinò, and Ioannis, who is sitting next to me. So I don't think I need to motivate to you why studying the economic effects of AI is important. The Collins Dictionary named AI the 2023 Word of the Year. It's considered to be the next great technological revolution. And there is a lot of hype about AI, but there are also concerns. There are several concerns, and one is about the labor market effects. And in particular, one of the pressing questions is the effect of AI on jobs. Will it complement workers or replace them? And it's an open question because on one hand we can think of AI as algorithm that improve decision making, and this is probably likely to be complementary to labor. It's likely to increase productivity and therefore employment as well. At the same time, in doing so, AI may replace, for instance, directly some business functions. But I think the main concern is that AI might be used basically to power automation. So we see a very recent application of ChatGPT to robotics, and I think the concern is that these intelligent robots that are coming may be used to automate more and more jobs. And so whether or not AI will complement workers or replace them, it's an open question, it's an empirical question. And the literature has started to address this question, but the literature faces two main challenges. The first one is how to measure AI. Unfortunately, there are no official statistics about the adoption of AI. And the second one is to identify causal effects. And in this paper, we try to make progress on both questions. And in particular, as we have already seen yesterday, there are several papers that try to guess what is going to happen in the future. And of course, this is a very important exercise, given the information that we have today. In this paper, we take a complementary approach. We look at what has happened already in the past, moving from the observation that AI, of course, it's generating a lot of hype now, but it's not an entirely new technology, and early adoptions of AI started around the early 2000s. So in this paper, we have to adopt some definition of AI, and our working definition is relatively broad, but we think that it captures the most important aspect. It's essentially algorithm applied to big data. And with this definition, we can identify early applications of AI, starting from search engines, personalized ads, recommendations, and so on and so forth. And then the next question is how to measure the adoption of these technologies. And the way we do it is by recognizing that in order to adopt AI, firms need very specialized workers with specific skills, in particular with the ability of using software which is typically used for machine learning and data analysis. And then we measure the adoption of AI as the increase in the employment in this type of AI-related occupations. And then we identify the causal effects on employment across US commuting zone using a sort of standard classical Bartik shift share design. But I will be more precise about this in a moment. So a preview of the main results, what we find is that AI adoption slows down employment. So this tends to support the view that AI seems to be used to automate work and so to replace workers. We find that the effect is economically significant. We find that it's mostly driven by adoption in services. Adoption is mostly, not exclusively, but it's more in service, in the service industries rather than in manufacturing. But the negative effects are in all sectors, which suggests that there are also spillovers across industries in the economy. We also find that the effect is quite heterogeneous across workers, and in particular, workers that are hit in a negative way, negatively affected by AI are low-skilled workers, workers without a college degree, middle-aged workers, and production workers. We do find some winners from AI, but these are in very specific occupations, and in particular, we find that AI increases employment of the top earners, the top 10% of the distribution of income, and workers in occupations that require a STEM degree. Okay, very quickly, the related literature is on these issues is quite recent. There are some papers that study the employment effect of AI in very specific occupations. And typically, they tend to find negative effects. This is the case for financial analysts, for freelancers. Then there are papers that instead look at more aggregate effects. Typically, those papers, they rely on measures of exposure to AI of different occupations. And we view this as a complementary approach. So this line of research focus on workers that are expected to be affected in some way. Instead, we use a measure of adoption, and then we see what the data basically is going to tell us about the effects. One limitation to some extent of these measures of occupational exposure to AI is that typically it's difficult to distinguish between whether the exposed occupations really compete with the AI or if the AI is complementary to them. And so also from a sort of theoretical perspective, the predictions are not very clear-cut. And there is also the issue that, of course, there is indeed a growing number of those indexes of occupational exposure, probably because it's difficult to assess the capabilities of these technologies, and the capabilities of these technologies are likely also to change over time. So we take a complementary route, which is instead to try to identify adoption and then see what the aggregate employment effects are. And the advantage also of our measure is that it's relatively easy to construct for a large sample. Okay, so let me start by showing you very quickly a simple theoretical model. The main contribution of the paper is empirical, but we write a simple model to motivate empirical analysis and also to show you what are basically the theoretical foundations for the regressions that we run. The model is as simple as possible, and it's designed basically to sort of microfound the empirical equations that we take to the data. So here the key unit of analysis is the commuting zone. So here we see the production function for industry I in commuting zone C. And in order to produce output, you need to perform a unit measure of tasks, X. And this task can be performed by either labor, L, or AI, A. Then you also need some industry-specific capital, KCI, and then the differences across commuting zones in the endowment of this industry-specific capital will lead to a pattern of specializations, differences in the composition of industries across commuting zones. And then the phi is a productivity parameter. There is also production function for AI, and so here in order to produce the AI input, you need some intermediate input. You can think of it as software, data, computers, and then you need some specialized labor, H. And then we define AI progress as an increase in the task share performed by AI. This task share is kappa, and so AI progress is an increase in kappa. And as you can see at the bottom of the slide, we also allow this AI technological progress to affect directly productivity, phi. We do not really microfound why and this type of technological progress in AI because it's not really relevant for the empirical analysis, but we want to be broad enough to capture all the possible effects that have been emphasized in the literature. So increasing the task share of AI, since AI is cheaper by assumption than workers, in itself has a productivity effect, increases output. At the same time, we also allow AI to increase directly productivity to capture this idea that in some cases AI may well be labor complementing, and so it may act as an increase basically in TFP. Then to derive the empirical predictions, we impose some additional simplifying assumptions. They are not crucial, they're just to simplify the analysis. So we allow for free trade across the commuting zones. We assume that all factors except the specific capital is in elastic supply. These allow us to focus on quantities and not prices. And then we assume that we start with an initial equilibrium with no AI at all. So kappa, the AI share, initially is 0. And then we can derive some empirical predictions. The first one show that we can measure AI progress with the change in AI employment, in the specialized workers used in the production function for AI. And then second, aggregating the labor market effects, labor demand at the commuting zone level, we can find predictions for the effect of AI. In this case, it's already measured as an increase in AI employment on overall employment in a commuting zone. And as you can see, the coefficient is potentially ambiguous because it has two components. The first one is the usual productivity effect. It has to do with the cost saving of AI and also the possibility that AI may directly increase TFP. If you believe Daron's calibration yesterday, this might be a small number. And then there is the displacement effect. Of course, here AI is also taking tasks from labor, and these, of course, tend to reduce the demand for labor in final production. So the sign of this coefficient is an empirical question, which is what we are after. And of course, if we want to take this equation to the data, one key challenge is the fact that the increase in AI employment at the commuting zone level is likely to be endogenous, and in particular it may be affected by shocks. You can think about demand shocks, which are likely to increase employment directly, but they may also trigger more investment in AI, and so they may generate a spurious correlation between AI adoption and employment. And so to overcome this problem, when we take this equation to the data, we will instrument essentially AI adoption at the commuting zone level by using not the change in AI employment at the commuting zone level, but taking the change in AI employment by industry at the US level. Given that commuting zones are small, each commuting zone should not affect AI adoption at the US level. Okay, so the data, we use data on 722 commuting zone. The labor market statistics and employment data are quite standard. For occupations, we need data on occupation, so here we rely mostly on the ONET database, and in particular to identify the AI-related occupations, we use a new section of ONET, which is called Hot Technologies, that lists software that is typically required for different occupations from job postings. And in particular, among all these software, we identify 54 software that are typically used for data treatment, for machine learning, and then we identify 19 AI-related occupations as occupations for which at least 2 of those softwares are in demand, so are required, and occupations whose main tasks fall within the domain of computer science, mathematics, statistics. And then we compute our measure of AI adoption as the increase in AI employment in a commuting zone over a certain period of time. Okay, so one example of probably the most obvious example of the AI employment is data science. And in terms of, so using this measure of AI adoption, then we can study what has happened to AI employment across industries and also over time. And there is quite a bit of variation across industries, and maybe it's difficult to read the table. You have the top 10 and the bottom 10 industries. But top industries are typically advanced services, including business services, software services, and including also some parts of the public sector, like national security and yeah. And instead, the bottom industries with little increase in AI employment include traditional manufacturing. AI employment has increased over time, and in particular, the increase has accelerated in the second part of the sample, so after 2010. Okay, so moving to the empirical specification, so it's a difference in difference equation, so we regress change in employment over population on our measure of AI adoption, which is a change in AI employment at the commuting zone level. And we do it, the specification is in stacked differences for the 2 decades, 2000, 2010, and 2010, 2020. And in all the specifications, we control for a number of fixed effects. So we have census division, fixed effects. We have decades, fixed time effects. And then we also include a number of controls that control for initial characteristics of the commuting zone, things like population, demography, economic characteristics. We also control for the two main shocks that have been studied in this literature using this approach over this period, namely the China shock and exposure to industrial robots. And we cluster the standard error at the state level. Okay, so here the coefficient of interest is this beta that captures the difference in employment outcome across commuting zones with different rates of AI adoption. Of course, the OLS is not going to deliver us the causal effect, because there might be unobserved shocks like demand shocks that may affect simultaneously both AI adoption and employment. And so for the identification, we use a Bartik instrument where we essentially combine, so it's a shift share instrument where the shifts are changes in industry US level AI employment, and the shares are the industrial composition of the different commuting zones. So here the intuition for this identification strategy is that the scope for AI adoption varies across different industries, and we measure it with AI adoption by industry at the US level, and then that industries vary in the composition of employment across industries for historical reasons. And so here, compared to the equations that we derived from the model, there are two main differences. The first one is that employment shares are computed for 1980, so way before the arrival of AI, and so they are predetermined, and the shares are not the changes in AI employment at the commuting zone level, they are for the US economy at the aggregate level. Okay, so the idea is that we will study the differential effect of exposure to AI across the commuting zones. Okay, so here you see a map with both the measure of AI adoption at the commuting zone level and AI exposure. So I don't have much time. I just want to say that there is quite a bit of variation, but also if you compare the two maps, you see that there is a clear correlation. So it seems that indeed AI exposure of the commuting zone predicts well AI adoption, which is going to be confirmed later on. So let's move to the results. So here the main result. So in the first four columns, we see the specifications without controls, then we add the controls. So in the first column, you have the OLS, and you see that there is already a negative correlation between AI adoption at the commuting zone level and employment. Then in the second column, you see the first stage, and you see that indeed AI exposure is a very strong predictor of AI adoption. And then you see the reduced form, and the fourth column is the IV estimate. And you can see that it's negative, it's highly significant, and the effect is stronger compared to the OLS, which suggests that indeed contemporaneous shocks may tend to generate a positive spurious correlation between employment and AI adoption. And then once we add the controls, we basically confirm all the results. In terms of magnitude, these effects are non-trivial. And here, of course, it's a differential effect. It's important to stress that. But basically, so if you consider compared to a commuting zone with no adoption at all, an hypothetical commuting zone, with the average characteristics and the average level of adoption, a commuting zone with no adoption at all would experience a faster employment growth by 0.6 percentage points over the sample period. Okay, so this result is quite robust, so we do many robustness checks. Of course, one concern could be that this AI employment, these workers, yes, maybe they work to some extent in AI, but they might also do other things. So here we consider also alternative definition of AI employment. We use a very narrow one, which uses only data scientists. We use another alternative classification provided by Anson, and we find very similar results. Then we exclude outliers, we exclude the COVID period, we do alternative clustering, and the results are very robust. We consider a number of possible threats to the identifications. This could be because of contemporaneous shocks that affect still employment and adoption or exposure, or trends. And we try to deal with these issues in different ways. So we compare commuting zones with similar changes in employment, with similar changes in adoption. We exclude outliers, we exclude industries with top shifts, or a commuting zone with extreme values of AI adoption. This could be a commuting zone that produce AI more than just using. We allow for different trends by playing with the fixed effects, so we can include state, time, fixed effects. We can also include the commuting zone fixed effect. In that case, we eliminate completely the cross-sectional variation. The identification is going to be only within commuting zone. Then we regress past employment on current AI, and we don't find any evidence of trends there. We include past employment growth as a control, and once again, the results are robust. So very quickly, in the final minutes, some additional interesting, I think, results. So here one concern is that this AI employment, once again, it may capture something else. So here what we do, we include as controls a number of Bartik shift share variables for capital intensity, software intensity, computer intensity, communication intensity, value added, and offshoring. And two main results. First, the main result on AI adoption is unchanged. And then adding these other controls that control for other type of technological variables, well, typically we find that these additional technological variables tend to be more complementary to labor. So sometimes we estimate positive effects for these additional variables, and once they are introduced, all of them in the regression, actually the coefficient for AI adoption becomes even more strongly negative. Okay, so finally, we try to dig deeper a little bit and try to better understand where the result is coming from. And so in the first column here, we compute AI adoption only within manufacturing, and we see that the result basically disappears. In the second column, instead, we compute AI adoption in the complementary industries, so outside of non-manufacturing, and we see that the coefficient comes from essentially the service industries. It's adoption in the service industries that is generating the result. Then we split the effect across the different industries of sectors of the economy, and here we see that the negative effects are, well, there is some positive effect on the primary sector, so agriculture, it could be because some workers that are displaced end up there, but for all the other sectors in the economy, the effect is again negative and quite significant, and most of these, the effect on employment is through workers exiting from the labor force. Finally, heterogeneity, and then I will basically stop. By skill and occupation. So here it's a bit, reading this table is a bit long, but let me summarize. Well, we find negative effects for low-skilled workers, and especially, and for production workers. For high-skilled workers with college, so as a whole, we find mixed effects. But then if we distinguish between workers in occupations that require a STEM degree, which is the column number 7, for them we find positive employment effects. And then finally, across the wage distribution, so here we compute the effect across the different quintiles of the wage distribution, and we find throughout negative effects that are sort of uniform, except when we get to the very top of the distribution. And indeed, if you focus on column 6, we see that it's only the 10% of earners that benefit in terms of employment prospects from AI. Okay, so to conclude, we propose a new measure of AI adoption, and we use a shift share for identification. We find that AI adoption slows down employment growth. The effect is driven by adoption in services, but the negative effect is in all the sectors of the economy, and it affects mostly the low-skilled workers, the middle-aged workers, and production workers, while those who benefit are the high earners and workers in a STEM occupation. So it's an economic policy, so we end with some possible policy prescriptions. So clearly promoting education in scientific fields might be a good option. Facilitate job-to-job transition if indeed AI generates some disruptions. Top earners gain, so maybe it could be a good idea to put in place a transfer system from them to the rest of the population to make sure that the shares are, the benefits are shared, and to try to promote AI applications that are complementary rather than substitute humans. Thank you.
Much, Gino. So, Axelle.
All right, so thank you very much for giving me the opportunity to discuss this very interesting paper. So to put it into perspective, let me start by saying that, does it work? Yes, that there's an emerging literature that's trying to assess the effects of the adoption of AI on labor markets. I will not describe it in detail because we have talked about it yesterday and today again. But in that literature, this paper stands out by exploiting heterogeneity across regions to measure the overall net effects of AI across sectors or across industries and across occupations. So to do so, they built a simple, flexible theoretical model that they bring the data using a standard shift-share design. So they're going to work at the commuting zone level from 2000 to 2010 to 2020. And they're going to use publicly available data, such as the census and ONET. So I'm going to start by very briefly summarizing the paper in one slide. So I will again describe the empirical strategy and summarize the key findings. So the empirical procedure goes in 3 steps. So first of all, they identify a set of occupations that they define as AI-related. So they have a definition such that the occupation has to require to use at least 2 softwares out of an AI-related list of softwares, and have to belong to a specific field, I would say roughly computer. So that gives them a list of 19 occupations, which include something like a database architect, but also computer programmers or web developers. With this definition of AI occupation, they then built a measure of AI adoption at the commuting zone level by measuring the change in employment in those AI occupations in that commuting zone. So you live in a commuting zone where suddenly there are many more web developers employed, then that's going to show up as a measure of AI adoption. Okay, and then they're interested in understanding how these changes in this, whether commuting zone, which experienced higher adoption in AI, also experienced boom or negative shock on the labor market. But of course, they are concerned with the standard endogenous concern that Gino explained, and therefore they are going to IV adoption with a measure of exposure, which essentially combines nationwide industrial shift with local industrial shares before the shift. Okay, so with that strategy, then their key findings are as follows. So first of all, they find a negative effect of AI on employment, which is essentially driven by the AI adoption in services rather than in production. And interestingly, this negative effect of AI is going to have, adoption of AI is going to have a negative effect for workers, not only in the tertiary sector, but also in the secondary sector. Their second batch of results has to do with the heterogeneous effect of workers. In a nutshell, they find that the effect is particularly negative for low-skill, low-income occupation, while it can actually turn positive for the high-skill STEMs worker and the very top-income occupations. Okay, so of course I don't need to convince you that the paper is very topical. It's also, I want to say that it's really extremely well done with a lot of robustness check, and the results are actually very robust to all the robustness checks that they actually conduct. So I am going to put on the table a list of comments or sometimes more open questions which have to do with the instrument, with the geographical scale of the commuting zone, also with the definition of the AI occupation. And I'll conclude with a few comments on the relevance for policy. Okay, so first of all, if I take a step back and I think about what is the effect of AI on the labor markets until 2020, so of course there's something, AI adoption is gonna have an effect that is ambiguous, and that really is the core of the model in the paper, in the sense that it can enhance efficiency of some jobs, but it can also result in job displacement. But before that, in a sense, there's another stage, which is really like the AI production, which is that when AI develops, it's going to stimulate jobs in some very particular sectors that actually sort of build the technology. And in a sense, the model is really more about adoption than production. But when we look at what are the top industries in terms of AI adoption, which are selected by the procedure, what we have is that in that list of industries, we have industries like insurance and finance, for instance, or electric power generation. But we also have industries that sounds much more like AI production than adoption, like computer system design, software publisher, scientific research and development services. So I wonder whether it would make sense to actually have a robustness where you actually exclude those industries which are more likely to actually produce AI. And I have read the robustness on the top 10 exclusion, but I think maybe something more specific could be done here. Now focusing more specifically on adoption. So here the focus is really about the adoption of AI and the effect on the labor market in a commuting zone. And the typical concern is that, you know, like in a commuting zone could be booming for any reason, which would drive up both employment in AI and non-AI occupation, and that would induce like a close correlation. Therefore, they are going to IV adoption with exposure, which means that they are going to, so a commuting zone will have high exposure if it already had a large share of employment in a list of industries, such that, again, computer systems, software publishers, scientific research. Okay. So technically, what does it mean? It means that, so if I look at the map of adoption that we saw very quickly, I have high-tech hubs, which are of two sorts, sort of. I have the old high-tech hubs, which like Seattle or San Francisco, and I have the new high-tech hubs like Boulder and Austin. So in Seattle or San Francisco, we'll have a high adoption, but also a high exposure, while Boulder or Austin will have high adoption, but low exposure. Okay, but then I may think that the effect of, the type of AI implemented and maybe the effect of AI adopted in these different regions may be quite heterogeneous. Why? Because I could think that in Seattle or San Francisco, I already had a lot of high-skilled workers working maybe for ICT, and then they switch their work towards more AI. While in Boulder or Austin, it's really about attracting new workers who actually migrate to these cities. Maybe they are younger, maybe they are just out of the university and better trained on the latest software. Also, I may even think that from the firm perspective, so a lot of the high-tech firms actually have offices both in, say, California and Colorado, and the way they actually allocate their teams or their research project between those two offices may not be random. And I don't know, maybe they try, they put more risky projects or maybe high-risk, high-return projects in places which are cheaper, like Boulder or Austin. So I wonder that whether, it would be kind of useful to have a discussion about what this instrument exactly picked as a heterogeneity, maybe with a bit more detail. Okay, then about the commuting zone. So when I was writing the paper, I wondered a little bit whether the commuting zone was really the relevant geographical area for AI adoption. Why? Because if I think about job displacements, so I'm going to take a really basic example. I think I'm the head of a retail bank and I want to implement a new algorithm that's going to be AI-based to maybe do some check of fraudulent operations. And so I'm going to hire a team in a particular commuting zone, which will be, of course, in AI occupation, and that may have a negative effect for clerks in local branches all over the country. So the commuting zone really, I'm not sure we should really focus so much about the adoption in the commuting zone on the labor market in the commuting zone. Instead, I think the AI exposure is kind of capturing exactly what you would think about, how I think about the effect of the adoption of AI, in the sense that it's really captured, like you have a lot of workers in retail banking, and then you may be more affected by the adoption of AI. So when I look at your reduced form regression, I think they are actually very significant with a very steep slope, and I think that's super interesting. But then it leads to another concern, which is maybe the endogeneity concern I'm worried about is not really at the commuting zone level, but at the industry level. In the sense that, should I be worried that maybe there's a shock in some specific industries, a negative shock to the labor supply, so that employment falls in those industries, and then as a way to, then as a response, the firms start to adopt more of AI. So in the same way that, like for the China shock literature, we try to instrument the change in imports at the national level by industry, by the change in imports in other countries. Is there something that could or should be done about this possible endogeneity at the industry level? But this is, I think, is beyond the scope of your paper. It's more like a general thought here. Okay, and then an additional comment that is more like looking forward. So of course, your analysis stopped in 2020, but after 2020, there's ChatGPT, for which, that also raises concern about job displacement. But when you think about adoption of ChatGPT, it's unlikely to be seen in sort of specific AI occupation skills. Why? Because if I think about again, to take a very basic example, if I think about the communication team at PLC, they were always understaffed for many years, and they wanted to expand and hire, but now that they have ChatGPT, it's actually a lot easier, and it's not so sure that they're going to expand. But using ChatGPT requires just using a browser, right? So it's really not a skill that's going to show up. But again, that's again a bit beyond what you're doing here. I had a small comment that I will skip for the interest of time. So I really like all the results about heterogeneity across occupation, and I think it would be nice to maybe, so I wonder whether the decomposition that you do exactly overlap with the standard routine, non-routine, cognitive, manual decomposition, and whether, Daron showed also other decomposition yesterday. It would be kind of nice to try to match, or to see how it compares. But just to conclude, so I think, so one thing that is a little bit missing for me in the paper is, so we see that the effect is negative and is significant. I still don't have a very, very clear idea about the magnitude of these effects. So you did mention one number today, but it would be nice to try to compare, across extreme commuting zones, how big is the difference in labor, in employment rates, and also, for instance, could I try to derive backwards-involved computation to get a sense of, so your results seem to predict that there would be an increase in inequality. That could suggest that indeed we would like to tax more and redistribute more, but I don't have a good sense of how large would be this increase in inequality, like what are the numbers we're talking about? Just again to understand how relevant that would be for policy, it would be sort of nice to do this maybe. But to conclude, thanks a lot. It was a very nice paper and really very well done.
Thank you very much, Axelle. So, Gino, do you want to take 2-3 minutes to answer, to respond, and then we collect questions?
Yes,
okay?
so thanks for the great comments. I think you gave us many things to think about. So let me go through them quickly. So first, you mentioned this issue that some of the top industries might be industries that produce rather than the industries that use AI, and this is a concern that we have in mind. So, and indeed, at some point, we exclude the top industries precisely because of that concern, and this does not affect much the result. At the same time, my sense is that keeping those industries in the benchmark specification seems to me a good strategy, because I think that having in your own commuting zone a lot of industry that produce AI may indeed foster adoption by others. Typically, we know from the literature that these local spillovers are pretty strong, and so by including those industries, we capture also this effect, the proximity with respect to those industries that create AI. Regarding the difference between old and new technology hubs, I think what you said is very interesting. The problem is that the new hubs, they happen within the sample period, so they're clearly much more endogenous, and so our approach is precisely to try to get rid of that, of those observations, because they might be contaminated by other things, so that there might be reasons why we see those apps and these new apps, and those reasons might have a direct effect on employment. So I think it's a very interesting question to study better those places, what happened. Also, they look like examples of successful adoption of AI, so I think they're interesting to study on their own. But for identification, we feel more comfortable relying more on identification based on predetermined patterns. So adoption in one place may have a nationwide effect. I totally agree. Once again, we tend to see in many instances that there are also local effects. And nevertheless, we do find the local effects. So if the effect would only be at a national level, this would go against our estimation. So I think this makes it even more interesting, the fact that we do find local effects. So industry level issues, so it could be that the different industries are subject to different shocks. And so we are, of course, to some extent concerned by that. So at some point we include a Bartik shock for value added that shows that the results is not driven by the fact that different industries are on different trends, and then this is what is driving the result. The routine, so I think among the controls we maybe Ioannis can confirm, I think we always control for the routine share of employment in the commuting zone, but certainly we could do more and try to distinguish also between manual, cognitive, tasks. And regarding the magnitude, yes, it would be nice to do more. So here, the identification that we use poses some limitations, so we can identify only differential effects. Over the sample period, actually, employment on average, where it was going up. So our data do not support this view that AI is creating massive unemployment. It's a period in which unemployment is going down and employment is going up. But nevertheless, what we identify is these significant and large differential effects. So these commuting zones that are more, in the end, data intensive, they seem to do worse in terms of employment compared to the rest. And we think that this is a very interesting result. It's certainly not something that we had a very strong prior on, but this is what the data is telling us. And of course, there might be different interpretations, but the finding in itself, to me, is interesting and important. So, but yeah, thanks a lot for all the comments.
So we have a few questions. We go like that. So start from Jan, Inga, Anton, Richard, and Juan. So short questions, so we can have. Thank you.
Yeah, I would argue that this finding of negative employment effects is really surprising. I mean, interesting, but also really surprising. And the reason is that, I mean, part of the negative effects we would expect within industry, right? If ChatGPT becomes very good in programming, then maybe we need fewer programmers. But from these sort of effects, you're abstracting, right? Because the explanatory variable is, for example, how many more programmers are coming into local labor markets. So sort of these within industry displacement effects you don't capture. And so then when I think it relates to some of the points in the discussion. So if there's sort of additional AI worker coming into a local labor market, why would I expect negative effects in that local labor market? I mean, on the one hand, these additional workers, they need potentially local services, right? They need to go to the coffee shop, they need to go to the supermarket. And then if I think about the negative effects of that, I would think about national level effects, not about local effects, right? Because probably these are occupations and industries that produce tradable services, not services that are local to the local commuting zone. So from that perspective, I'm a little bit puzzled, like why we would get negative effects. And of course, I mean, you previously said, well, this is what the data tells us, and I think that's very interesting. But conceptually, I find it surprising. Thanks. And maybe you have some comment on that.
Yeah, so it's, I basically agree with you. I think there are reasons to look at local effects. One concern expressed in the literature is that AI, which we think of it as algorithm, but in the end, AI can also be used to implement more automation, and this is maybe what we are seeing. So even at the local level, if you substitute you adopt automated cashiers in stores, I guess you need some technicians to supervise, and you fire some workers. So that's something that could be happening. It could well be that we find a significant negative effect on manufacturing, which is not the main industry that is adopting these workers, that is hiring these workers, which once again may suggest that there are spillovers. So if you have a strong local supply of AI, this may help your manufacturing firm to automate, and that could be. Ideally we would like to explore the channel more, but the finding is pretty robust. I think it's interesting, and as I said, it's open to interpretation. But yeah.
Thanks.
Just for maybe the sake of efficiency, let's collect the questions and then you
okay.
Answer to all of them maybe. And there is also Isabel that has kept my fault. So.
Hi, I'm Inga Heiland. Thanks for the presentation. I'm also concerned about these trends at the national level, and basically very closely related to the previous comments. This finding that it's the adoption in the services sector that's driving the results at the local level could be explained by the manufacturing sector being more exposed to the adoption at the national level, because manufacturing goods are traded, but services are more local. Second quick comment is about offshoring. So you have a control for exposure to offshoring, and I was wondering whether this is offshoring of manufacturing inputs or services inputs, because the second seems more relevant, but is quite difficult to measure. Thanks.
Thank you.
Yeah, I also thought it was a really interesting paper, and I guess one of the things that makes it most interesting is that these effects took place in data up to 2020, which was before the current big advances in AI. Before the 2020s, the AI systems were pretty narrow. What we have now with language models is much more general purpose AI. And I guess that means we should potentially expect much larger effects now. Now, one of the places where this kind of has different policy implications is for the narrow AI systems of the 2010s. I think it makes much more sense to kind of push this notion that we need more education than it makes now, because in some ways a lot of computer scientists suggest that now the safest careers may actually be apprenticeships or something like that, that is not exposed to cognitive automation, but more to that is more engaged in physical tasks. And then piggybacking on the two comments before me, maybe explicitly distinguishing tradable versus non-tradable industries makes a lot of sense. Thank you.
Yeah, I was a little bit surprised that neither Gino nor Axelle referred to the big IMF study that came out in January of this year, so a few months ago already, it takes a totally different approach. As you would expect from the fund, it's a big cross-country exercise, and it is not essentially regression-based, but it goes fairly deeply, and of course it stresses the two dimensions of the degree of occupational exposure and the degree of complementarity given an occupation. And I'll just finish by saying there's a lovely little box at the end of this paper which shows on one axis, the degree of complementarity that they attribute to a particular occupation, complementarity with AI, and on the horizontal axis, the degree of exposure. Now, where would you guess economists come? We come slightly below the median on complementarity, interestingly. We come fairly substantially above the median in exposure. You may take that as you will, but if you think about at the same level of complementarity, they put dancers, right? But dancers are not very highly exposed to AI, and so on. It's fun to look at this diagram and to go, obviously very interesting to go into how they constructed it, and it seems to me, although as I say, the approach is totally different from this paper, nevertheless, the underlying issues and the underlying stress on the one hand, and the conclusions effectively are quite similar in terms of the impact on different occupations and so forth. So you clearly have to take account of it in the paper as it's finally written.
Yeah, but, nice paper. I like it very much. But the big issue is the national versus local effects. And here, just I see some similarities with the literature about the impact on immigration on labor markets. From this literature, what we learn is that depending on labor mobility, the impact could be very, very, very different. So now we have algorithms and robots instead of immigrants coming, but the transmission could be something similar. So I wondered, what do you need to assume about labor mobility across commuting zones for the identification strategy to be robust, and how, again, national effects could be very, very different depending on labor mobility.
Hi, thanks very much. Very interesting. So I guess everybody has a bit the same type of comments, like, because we're all very surprised by your results. So I would say that there is a big difference with respect to the impact of immigrants, which is that these tasks that you're talking about are probably the most tradable type of tasks that we could imagine. So if we think about like actual adoption of those, there is no way any of those firms is going to produce those tasks internally with their own algorithm. So this is completely outsourced task, which I think is a very important aspect to point, including within your framework. It's not entirely clear to me that your framework is taking this dimension into account. So I understand that the contribution is empirical, and you do have those kind of local effects that are very interesting and puzzling. But again, the dimension of the tradability of those tasks is something that I think is very important. And then it becomes even more important to be very specific about the variability that you're using and basically the story like at the heart of those local effects.
You can take 4 or 5 minutes to respond.
Okay, so thank you very much. Great comments. Yeah, there are some common themes. So let me try to respond. So yeah, there is one concern about local versus national effects that seems to be common among many comments. Yeah, I think it's an interesting point. It's yeah, well taken. It could be that this is particularly relevant for manufacturing, as it has been suggested. So yeah, I think so. Yes, ideally we would like to dig a bit deeper in the result. It's not with the data that we have. There is only so much we can do. So we have been thinking about these things, and maybe yeah, this will motivate us to write other papers trying to identify the specific channel. So yeah, I'll leave it a bit open. So regarding other questions, so for offshoring, yes, we do control at some point. It's in manufacturing because it's the only variable we have. I think it would be nice to try to control for service offshoring as well. So then, so yeah, the AI is changing. So our results are, of course, backward-looking. So, and indeed, I think there is value in trying to predict what is going to happen with the new generations of AI. Effects might be larger to some extent, yes, because it has more scope, more potential. Some results might be different. This is also possible. But we see a lot of speculation, and again, I think it's a very important and useful exercise. But here we try to look at what has already happened, and so in terms of policy recommendations, of course, it's a fine balance because what has happened in the past might be different from what will happen in the future. So our results seem to suggest that, you know, if you want to be shielded from these disruptions, the best thing to do is to invest on a STEM degree. I personally think it's a good bet. I'm not so convinced that in the future we will all do, you know, creative stuff. My sense is that we will. The more we use these technologies, the higher is the demand for people who are able to understand it, to work with it, to change it. But of course, the future will tell us. It's an open question. So IMF study, I think I've seen it. That's so the point, if that's the paper I have in mind, of that paper is precisely the fact that with this exposure measure, you need to be careful because exposed occupations might, in certain cases, actually be complement with AI. And in fact, they find that high-skill occupations in those scores, they tend to be more exposed than the rest on average, but this exposure is actually of the good type, so it's complementary. So this is completely in line with our approach, and our approach takes a very different route. So we don't take a stand on who is exposed or not. We know that building these indexes is, of course, again, a very useful exercise, but it has some limitations. They're all, to some extent, questionable. They're based on assumptions. We try to be a bit more agnostic, so that's our approach. Yeah, so the assumptions that we need in order to identify our local effects. So actually, labor mobility works well for us because we focus on quantities, so we focus on employment, not on wages. Labor mobility may change dramatically the impact on wages. But indeed, our model, in order to deliver in the simplest possible way the empirical prediction, assumes that labor is in perfectly elastic supply. This could be because of the endogenous labor force participation, but it could also be because of free mobility between commuting zones. So that opens the door to other issues. But the point is that the labor mobility between commuting zones will not change our identification and our empirical predictions. Once again, if there is labor mobility, if a commuting zone is hit by a negative shock due to AI, workers will leave. So there will be a strong effect on employment, which is exactly what we observe. So yeah, thank you so much. And once again, the local versus national effect, I think it's one of the puzzles that emerge from these studies. We want to study it more, to understand it better. The literature is full with evidence of local spillovers, local effects. So there might be something like that going on, but for sure it's something that we would like to explore more in future work. And once again, yeah, if the effect should all be at the national level, we shouldn't be finding anything. So the fact that there is something, maybe it's a puzzle, but it's a puzzle that suggests that something is happening.
So thanks so much, Gino. It was great, good session. So we go to a very related paper by Juan and co-authors, and then discuss by.
So thank you. This is a joint paper with Stefania Albanesi from University of Miami, Ana Lamo and Antonio Diaz from ECB, and Alena Wabistch, who is a PhD student at the University of Oxford. Thank you very much to the organizer for inviting us to present the paper and to the editors of the issue for providing comments on a first version of this paper. As Gino said, I don't think there is a need to motivate to study the relationship between new technologies and labor markets. So let me skip the slides about motivation and go directly to how do we study these relationships and how we do it the way we do it. Okay? So I'm not getting used to. So what we do in this paper is to explore the link between. It's reacting too slowly, maybe.
You need an assistant.
Yes.
Not an artificial one.
Yes. So we look at the links between AI-enabled technologies and labor market outcomes in 16 European countries over the period 2011 and 2019. Okay. So why 2011? First, labor market outcomes. There is a big difference with the paper by Gino. We look at the distribution of employment across occupations. not at the aggregate effects on employment. And we look at the impact on relative wages, not on aggregate wages. Okay, so the focus is different. Why 2011, 2019? Well, before we cannot do much because there was a big change in the international classification of occupations in 2010, and then it's very difficult to compare data before and after 2010 when you focus on occupation at a high level of disaggregation, as the way we are doing it. Why 2019? Well, you know what happened afterwards, and it's true that we are living aside generative artificial intelligence and the new developments, but these are very, very new, and data on the impact of these new developments on the composition of employment, which is the thing that we want to look at, are not still available and probably are not still useful to answer the question. Why we focus on occupations? Well, the leading framework to study the impact of technology on employment these days is the so-called task-based framework that Daron presented yesterday and that Gino is using as the basis for his analysis. So this framework speaks about impact on occupations. So it seems natural to focus on occupation. Of course, you can learn a lot by looking at variation across firms. And there is a recent paper by Philippe Aguillon and co-authors showing that the main impact of new technologies, negative impact of technologies on employment is in those firms that don't implement new technologies. So it's firms implementing new technologies, those who gain employment because they become more competitive and so on. And also you can look at variation across geographical areas, and we just saw an example, a state-of-the-art example on how to look at these variations, and we just discussed the shortcomings of taking this approach. So this paper looked at the variation across occupations. Why Europe? Well, one might think that the impact of new technology depends very much on the institutional architecture of the labor market, and also on the digital infrastructure and institutional characteristic of each country. So there is something that we can learn from looking at cross-country studies, and that's why we try to collect as many countries as possible. And finally, we got these 16 European countries, 15 euro area and the UK. Compared to the paper that Richard just mentioned about the IMF, here we are looking at hard data. We are looking at what happened to employment shares and relative wages during this period. In the paper by the IMF is more speculative. They discuss what is the degree of exposure, the degree of complementarities of different occupations, and then they construct what they call the Artificial Intelligence Preparedness Index, which is a composite index taking into account all these institutional characteristics that I mentioned before: digital infrastructure, human capital, labor market institutions, and so on. Okay? Here just we look at hard data on employment share and relative wages, and we do it in a very descriptive way. I mean, we cannot claim that we are going to identify causal effects. This is not the purpose of the paper. I think it's very difficult to identify the causal effect of artificial intelligence on either aggregate or relative employment, mostly because exposure could be a good thing or a bad thing. exposure could be a danger of displacement, but also could be a potential for productivity gains if exposure implies some complementarities. Just as Richard mentioned, the degree of exposure and complementarity varies a lot across occupations. Okay, so this is very descriptive. And what is the lessons that we can take for this descriptive analysis? Well, mainly the big patterns in the data, the comparison across countries, and after all, if you don't see the smoke, why you should care about the cause of the fire? Okay, so this is the main attempt of the paper. Given that what we see in this period, at the difference across countries, is there a big reason to be concerned about the displacement effects of new technologies? This is basically the answer that the paper tries to achieve. So to do this, you basically need labor market data, which are simple to collect. From the European Labor Force Survey, you can get wage share, employment shares, and relative wages. To some extent, I will mention later on what is our measure of relative wages. The problem is how you measure exposure to artificial intelligence. Here, we do not innovate. We just take two measures that people have used from papers by Webb and by Felten. And to some extent, this way of looking at the exposure to artificial intelligence fits very well with the so-called task-based framework, and is the origin of the type of measures that now people are using for generative artificial intelligence. The measures that Darons mentioned yesterday about the exposure to generative artificial intelligence somehow are descendants of this way of measuring exposure. Okay? Basically, what he does is to take patents descriptions and description of jobs from ONET, and from there he tries to find an overlap in the textual definition of the patents and of the jobs, and from this textual overlap, he constructs an indicator of exposure to artificial intelligence. He also used a survey asking a sample of US workers in each occupation what are the typical work activities that they are required in their occupations. A similar way is the Felten indicator of exposure to artificial intelligence. Instead of using patents, they use reports by the Electronic Frontier Foundations, basically about what kind of tasks can artificial intelligence perform and what are the progresses in artificial intelligence in different dimensions. Okay? And again, using a mapping from the reports and the tasks described in these reports and the ONET classification of occupations, also with some survey responses about what workers do, they construct another indicator. Okay? They somehow refer to different aspects of artificial intelligence. And in some way, they measure different things or different components of what the first phases of artificial intelligence development was about. Felten is probably a better indicator of the exposure of workers' abilities to technological advancements, as reported by the Electronic Frontier Foundation. What instead it probably reflects better the ability of machine learning algorithms which somehow overlap with the workers' tasks. So in some sense, they measure potential impact of artificial intelligence on different dimensions, on different characteristics of the different components of the occupations. Okay? And again, I want to stress this is potential impact, it's not measured impact. So it's only potential. We don't use changes in employment as Gino to measure the impact of artificial intelligence. So, as I said, once that you have the indicator about exposure to artificial intelligence, getting the data for labor market on employment shares and relative wages is not that difficult. You just go to the European Union Labor Force Survey and you can get employment shares. You can also get relative wages, but relative wages at the level of the segregation that you want to go, which is 3-digit, is only from rankings, is the percentile position in the wage distribution. So what we are using for wages is not a cardinal measure of changes in relative wages, it's only a change in the ranking, in the percentile distribution of wages, which is important for the interpretation of the result that we are going to see later on. Okay. So once that you have the two sides of the equation, then what you do is just construct different cells. And here what we do is to construct cells by merging occupations and sectors. We have 6 sectors and about 100-something occupations, depending on the measure, web or Ferriere. So we have a cell which is the employment share of occupation I in sector J. In fact, it's the change in the employment share of occupation I in sector J over the period 2011-2019. And the same for relative wages. Again, with the caveat that the change in relative wages is a change in the ranking. No, it's not a quantitative change. The technological indicator used by Felten and by Webb are referred to the US, and they are taken from ONET, which is a description of occupation in the US. Okay? So to do the analysis for Europe, you have to assume implicitly that the occupation in the US is the same than in Europe, that an economist in the US do the same thing than an economist in Europe, which is controversial.
What about dancers?
And secondly, we do something else, which is to weight the indicator, the technological indicator, by the employment structuring in each country. So we convert the technological indicator from a cell-based indicator to a worker-based indicator. Okay? In the appendix of the paper, you can look also at regressions without weighting the data, and qualitatively, there is not much difference. Okay. So I will present you the results. And for presenting the results, I will present first the pool sample, what we get from the pool sample. I then will partition the sample by age groups and skills, and then I will look at the differences across countries. So what I am going to report is very simple. It's just you take a regression like the one that you have at the top of the slide, which is the change in employment share or the change in relative wages across cells in sector occupation and country C, and regress that on fees effects, country and sector fees effects, and the measure of the technological position, and I will report the beta coefficient. Okay? If beta is negative, it means that those sectors or those workers more exposed to the employment share of those workers more exposed to artificial intelligence has decreased. If beta is positive, it means that the employment share of those workers more exposed to artificial intelligence is higher. Okay? So I will show you now some graphs with the beta coefficient from different specifications of that equation and from different samples. This is the result from the pool sample. What you see is that beta is positive, is statistically significant, and it's also economically significant. So changing this position to artificial intelligence alters significantly the composition of occupations. You see that the result is positive for both indicators, the wealth indicators and the Felten indicator. Okay? Let me say that the two indicators differ when you look at the top and the bottom occupation in the distribution of exposure. They measure different things. When you look at some of them, when you look at Felten, you will see mathematicians, programmers, and so on the occupation more exposed. When you look at WET, you will see agricultural workers more exposed than mathematicians and statisticians and computer programmers and so on. But despite the difference at the top and at the bottom, the correlation across the whole distribution is rather significant. The Spearman coefficient is 0.64. So although they measure different things of artificial intelligence, they are positively correlated. And as you see, the results with weighted data, with unweighted data, tells you that there is a positive association between AI-enabled automation and changes in employment share. Then you can partition the sample and look at different groups. We look at differences across some robustness check, taking away some occupations and different specifications. Overall, you get the same qualitative result. You don't see many changes in the beta coefficients when you exclude managers, when you exclude professionals, when you exclude technicians. So there is something in column 2 which is a much lower coefficient when you exclude professionals, but overall you get this positive association across the board. Okay? So there seems to be some group which are important, in particular professions, which is the major group 2 in the ISCLO classification. And these are professionals with a high level of knowledge and experience in the fields of physical and life sciences and social sciences and humanities. Okay? This is also consistent with the results that I'm going to show you when we partition the sample by skill levels. As for wages, we don't get that much. Okay? We don't find any significant association. There are 3 explanations for this. One is that we are not using a good measure of relative wages. As I said, this is changes in rankings, not euros. The second one could be a supply story, is that the increase in demand caused by artificial intelligence in some occupation is matched by an increase in supply. We look at changes in the increase of supply, labor supply by specific fields. There is not much information about this in labor force surveys. When you look at data from educational databases, what you see over this period is that the change in university graduate by field have not changed that much. Okay? So you don't see a big difference in the proportion of STEM students in 2019 versus 2011. So there could be a supply story, but the data that we look at do not seem too confident on that story. Okay? They do not say that the change in the labor supply by STEM fields is taking pace with the changes in demand. And finally, the third explanation, maybe my favorite explanation, is that, well, in Europe, labor markets are very rigid. The changes in the distribution of wages takes a lot of time to take place, and so on. Okay. So I could talk about the comparison of this result to the results in other studies, mostly for the US, and the results by Gino. As I said, one important caveat is that we are looking at the composition of the employment, not at the aggregate employment. I love the skill and the age distribution. Basically, we divide the sample in 3 terciles: low, medium, and high skill, young, medium, and old workers, and look at the association between exposure and changes in employment shares and relative wages in each one of these samples. Okay? And what we see is that is in those occupations in which there are more young workers and high-skilled workers where the association is strongest. Okay? So the positive association between employment share and exposure to artificial intelligence is much bigger in those occupations, among those occupations in which there are young and high-skilled workers. Okay? Okay. And finally, across countries, there is some heterogeneity across countries, as you might expect. For wages, again, there are no effects, whatever the country you consider. For employment, depending on the measure that you use, you get positive effects. Just let me go to this graph where you have the coefficient from the both specification, and you see that the majority of countries are on the top right quadrant, which is positive coefficient for both indicators. There are a few countries with confusing results: Italy, Greece, and Denmark. But typically what you get is that regardless of the measure that you use, you get a positive association in most of the countries. Okay? And finally, we make an attempt to interpret this cross-country heterogeneity. We have a few data points, 16 data points, but we correlate this measure of association between artificial intelligence exposure and changes in employment shares with some indicators of the institutional configuration of the country that might affect the effects of artificial intelligence. And what we find is that our positive association between artificial intelligence and employment share is positively correlated with digital infrastructure, what the IMF study called preparedness for artificial intelligence, and is negatively correlated to employment protection legislation and degree of competition. Okay? Measures of human capital are positively correlated. So countries with higher human capital display a higher association between artificial intelligence exposure and gain in employment shares. Okay, so what do we conclude about this? As I said from the beginning, this is very descriptive. This is just providing the patterns across 16 European countries. Our interpretation of these results is that the artificial intelligence, or at least the early phase of artificial intelligence, looks very much like the skill bias technological chain hypothesis that we used in the 80s and in the 90s to talk about technological progress. Okay? So it seems that so far there is more complementarity than displacement effects, and so far, if you are more exposed to artificial intelligence, you have a higher chance of seeing gains in employment, relative employment, than seeing displacement effects. There is much work to be done, and to explain heterogeneity across countries, as I said, the paper by the IMF and the initial signs that we are getting from these numbers is that probably human capital and regulation of labor market matters a lot for the diffusion of artificial intelligence and for the effects of artificial intelligence. And that's it.
Thank you so much. Jan, it's your, the floor is yours.
Great. I guess I need a pointer. Yeah. Okay. Thanks. Okay. So this was a really nice paper to read. Still, this discussion is going to be a bit of a risky proposition for two reasons. The first is, if I understood correctly, you fired us panelists yesterday. So that is, of course, always risky if you ask your employees to give public presentations after you fire them. And the second is my glasses broke this morning. So by chance, I had one contact lens, but not two. So I'm half blind. So I don't see my own slides very well. So we'll see how that goes. So yeah, so just very briefly to summarize, the users, there's the second screen, thanks. Uses the EU labor force survey 16 countries, studies the association between labor market outcomes and AI exposure across these sector occupation cells. And there's also, you didn't talk that much about it, but there's some conceptual background, combine a task model of production with a model of wage determination. And so, yeah, this is a very comprehensive, very well-written study on the potential labor market impacts of AI adoption. It's really easy sort of to read and to digest, and so I enjoyed reading it very much. Main findings: positive relationship between AI exposure and employment growth. That's driven by occupations with higher proportion of young and high-skilled workers. And perhaps surprisingly, no wage effects. Okay, and I'm going to come back to that finding in my discussion. So the first topic I want to discuss is what type of shock are we actually measuring here? So I think what makes this paper special is that it really tries to estimate what is the association between AI and employment outcomes, rather than estimate it using actual data, rather than to somehow forecast that based on some assumptions, right? So for example, that differs from what we've seen Darren Acemoglu doing yesterday. So this is not so much based on assumptions and structure. This is really trying to use actual data to see what is happening. Of course, the potential downside of that is that this forces us to use past data, right? So by the very definition of the exercise, this is a little bit backward looking. Here the data is from 2011 to 2019. And I guess the question pops up, and not just in this paper, but I think a lot of the papers that we've seen in this workshop is, what are we actually then capturing that? Given that a lot of the boom in AI is a very recent phenomena, so what are we capturing if we use these past data? Specifically, one thing I'm wondering, is it sort of really AI, or is it sort of more automation in general? And or put differently, is this a contribution really very specifically on AI, or is this still very related to this more established literature on automation, routine employment, and so on? Okay, and I think Juan, you are very aware of this. I think the language you use in the paper, I think, reflects that, and that there's of course a little bit of ambiguity what we exactly capture here, but it's a point to keep in mind. So here are some of these heavily exposed occupations according to these two different AI measures. And so one question here, of course, is how reliable are these measures? How well do they pick up AI exposure? And not only how reliable do they pick up AI exposure, but also how much do they correlate potentially with other things that are happening across these occupation cells. And so one potential concern here is that, for example, this measure by Felton, it's based on occupation-specific skill requirements, such as things like verbal abilities. And then the question is, of course, whether these relatively broad abilities, whether there are other trends on the labor market that affect the employment shares of these different abilities. So one example, for example, this work by Deming, who shows that, for example, social skills are becoming increasingly important in the labor market. And so I think there's a risk, of course, here that we are picking up some of these broad trends, not just the sort of the AI exposure specifically. The two measures are positively correlated, but not that strongly. The question is whether that's, I think in the paper you sort of try to see that positive in that. So kind of, I think you emphasize that, well, this means that we are capturing very different aspects of AI measures. So it's kind of makes it more complete having these two measures. And that's certainly true, but it's of course also reflects that it is actually very hard to measure AI exposure. And you know, the best we can do is have these different measures. But of course, there's always sort of a little bit of a question mark in what exactly we're capturing. One thing that might be useful is to see how robust the findings are to trying to correlate for other type of shocks. For example, these more traditional automation shocks related to routine shares, or for example, trade exposure shocks that also have a lot to do with tasks and occupations. I think, Gino, you did that in your presentation, right? That you try to sort of see whether other shocks sort of would take away some of this variation. I think something similar could be done here too. Now, one sort of interesting question is sort of, is this like a descriptive paper, or is this like a causal paper? And I think in the paper you're very clear, there's some parts you're very clear that this is descriptive, not causal, maybe for the issues we discussed on the previous slide. Of course, still sometimes the language drifts a little bit into causal territory, right? For example, use the term effects. Actually, I do that as well throughout my presentation. It's kind of not avoidable to some extent. And so I think this is a balancing act. You know, I'm not the editor, so I'm not, thankfully I don't have to sort of decide how I would do this. I think it's fine, but I think this is of course one tension in this paper, that sort of how much do we stress the descriptive aspect and how much do we stress the potential causal implications. I mean, from a descriptive perspective, I think it's clearly interesting, and I think that could be motivated a bit more explicitly, right? Like, why are we interested in the descriptive evidence? And so, for example, I find it clearly interesting to know whether occupations that are more exposed to AI, whether they gain or lose employment, right? This might not be causal, but if you think about how much we should, for example, worry about workers in those occupations, that's clearly an interesting question to answer. And of course, a second motivation might be that this is maybe a first step towards a more causal analysis. And so I think the paper could spell this a little bit more out. Why are we excited about these findings? On the employment effects, you emphasize that this differs from the US evidence. You also showed us that the employment effects vary a lot across countries within your study. I'm wondering if that's something that is really problematic in any case, because if the interpretation here is mainly descriptive, not causal, then we are not trying sort of to estimate the same parameter, the same causal effects in different settings or in different countries. And the idea that employment trends differ in different countries is of course very intuitive. So I think you give some motivation there, but I don't even think this is particularly problematic. On employment effects, one question that could be interesting to, I don't know if you can really do something about it, but if maybe it could be discussed, is this distinction between the cell level effects, which are sector occupations, and this question of what happens to workers in those cells, which we could call worker level effects. And I think there are good reasons to expect that these could be very different. So for example, incumbent workers might struggle to adapt to AI, and be replaced by workers, maybe more younger workers, with more complementary skill sets. So whenever we have sort of this technological change, yes, this might change employment in the cell overall, but there might also be a lot of churning. And from that perspective, AI adoption could be bad news for incumbent workers, even if employment in the cell increases. And I think we do see this kind of contrasts in other type of economic shocks, such as immigration trade, that sometimes sort of these aggregate or cell level effects can be very different from the worker level effects. And I think that might deserve some attention. You talked about this lack of wage effects. It's very interesting. This is one of the figures we saw. So we have these positive employment effects in most countries. The wage effects are clustered around 0 and relatively small. And so you provide some potential explanations, for example, related to collective bargaining, shifts in labor supply. And I think these are plausible. But I'm wondering if there could be another explanation, which is compositional changes concealing these wage impacts. And that's, of course, partially related to this idea about churning. So if AI exposure brings in different types of workers, for example, younger workers, well, younger workers have lower wages. So thus mechanically, there might be these compositional changes might sort of either increase or decrease the average wage in the cell. And a second story here could be that if you have a positive labor demand shock, which seems to be sort of the case here, that you have employment increasing in the cell, well, maybe that pulls in kind of the marginal worker, right? So those workers who were on the sort of on the verge of getting a job, and now because of these positive shifts in these cells, they get into employment, and these marginal workers are probably the ones with lower wages. So so there is sort of reasons why you might precisely expect that these compositional changes are hiding these wage impacts because they sort of bias these average wages downwards. That's not a new argument. I think there's a similar argument being made in the macro literature on this question of why don't we see strong wage responses over the business cycle. Same argument, could be compositional changes, and I think this could be an interesting avenue here as well. Now, how much you can do about that is another question. I think we talked about it briefly before, that you said, well, the wage data is not very good. I mean, of course, you could, try to detect such compositional changes. You could say, see if there's changes in age structure, for example, in these cells. Maybe you could also residualize wages against observables, things like age and education, which is quite often done in studies that don't have panel data, right? If we have panel data, of course, we could control for individual fixed effects, and that would probably be the stronger design. Just to conclude, I mean, one theme here, I think not only in this paper, but also in the other papers, is that it's very hard to identify causal effects, right? So, I mean, even, your specification, even if we think that it's fully causal, we have all these country and sector fixed effects, right? So a lot of the impacts would certainly be eaten up by these fixed effects. So we're only identifying some sort of relative effects within occupation sector cells. And so to me, it's really hard to see how can we do good causal analysis in this setting. In your paper, you mentioned firm level event studies, that this would be interesting, and I agree that this could provide very targeted evidence, but that of course would be very distant from sort of the aggregate effects of AI exposure. And so it seems that whenever we sort of use these more local designs, including we had the same discussion about the regional designs, we need to somehow, even if we're able to get these local estimates, how do we extrapolate from that to say something about aggregate effects, which of course at the end of the day is the more important question. So this sounds really hard. Of course, the upshot of that is that providing descriptive evidence on this question is really valuable, precisely because it is so hard to get good causal evidence here. And I think this paper is sort of a really nice step in showing some general trends that are happening in response to AI exposure in a very comprehensive manner. And thanks for being the discussant. I enjoyed reading this paper. Thanks.
So much, Jan, for the discussion. So we have like 50 minutes. So do you want to respond briefly to Jan, and then we collect?
Yeah, very briefly. So thank you, Jan. Very useful comments. So let me just react very quickly to some of them. First thing, is it automation, what we are measuring with this indicator, or is something else? Well, in the presentation, I focus mostly on the artificial intelligence indicator, but you notice that in the paper we have a third measure of exposure to new technology, which is software, trying to see whether digitalization also have the same effects on, forgive me for using the word effects, on the employment and wage distribution. And what you see in the results of the paper is that it's not software, it's not digitalization, it's something different. Okay? What are we measuring? What type of shock are we measuring with these Felten and wet indicators? I agree, measuring artificial intelligence exposure is very, very difficult. Let me tell you what I think is the main drawback with these measures, which is, well, I already told you because this was my question yesterday to Darren. I mean, when you do this, you focus on tax, but a job is not tax. There are simple and complex jobs, and the combination of tasks within each one of them is very, very different. So the exposure to artificial intelligence depends not only on the exposure of each task to artificial intelligence, but also on the combination of those tasks for each particular occupation. Okay? And this is something that, to my best knowledge, no one have tried to capture with this indicator, and probably is the next step in this industry, try to do this combination of simple composition effect. Compositional changes in wages, you are right, this is something that we have to look at. Country heterogeneity, not the same parameter across countries when you look at this beta and so on. Well, this is the tension in applied economics always, okay? So, between identification and general equilibrium effect. If you go for identification, you have to be very, very precise about the parameter you are estimating. But the general equilibrium effect depends on the combination of many different parameters. In this case, it's exposure, digital infrastructure, how the labor market functions, and many, many other things. So you have to go for one of the streams in this trade-off. We go for the general equilibrium effects and try to look at the overall effects on the employment and wage distributions. Yeah, and for that we have to neglect identification, and we have to forget about identifying each particular parameter of the regression we are estimating. But again, thank you very much. Very, very useful.
Okay, maybe I can start. So this is a question which maybe is a bit general to the few papers that we've seen on the topic. I'm an outsider of this literature, but what I understand is that now the literature is a bit like consolidating on different ways of measuring AI exposure. And I agree with Jan, it would be very interesting that somewhere in this special issue there is a bit of a discussion of what tasks we're talking about and how much overlap there is between those different classifications. So I understand there are two main classifications that you're using. Gino is adding a third one. And the question is a bit like how much overlap there is. And the reason why I'm asking is that the way these things have been presented is that you're testing with different measures, and then the fact that results are robust across classification seems to be good news. But I was actually wondering the extent to which this is good news, in the sense that if you think that we are talking about very specific tasks that are likely to expand dramatically over the next few years, then you would expect that the impact on employment or other outcomes is very specific to those tasks. The fact that basically results are not varying much across classifications might mean that we are capturing some more, I don't know, broader trends. And so, yeah, I was wondering while listening to Jan whether we should think of this as being good news, that everything is robust to the way we are measuring this, even though we are trying to capture something that is very specific.
One quick comment and one broader question. The quick comment is that I wasn't too surprised by the concordance of results using the Felten and the Webb classifications because you said the rank correlation coefficient was 0.64. That's fairly high in my universe, and it seems to me that it's not at all surprising that we get these relatively similar results. The much broader question is coming from a pure consumer. This is, as most of you would know, it's nothing near my field, and I'm not even necessarily a terribly well-informed consumer. So I'm learning a lot here. But what I'd really like to know from both Juan Francisco and Gino is what you found in your work that actually surprised you. What's counterintuitive here? To me, a lot of what I've heard is, if I sit back as armchair economist thinking about these things, knowing very little, I come out with priors that have not been too disturbed by what you've said, but maybe I'm thinking about it wrong somehow. And you started from, you yourselves will have a better feeling for what it is that surprised you in your results. What did shake your intuition a bit?
Well, I agree, Isabel. We definitely need a better representation of exposure to artificial intelligence and probably clever ideas about how to measure complementarities. Probably one way to go is this distinction between simplex and complex jobs, and the combination of tasks within jobs could provide some indicator of the degree of complementarities. But there could be something else. Richard question, what is surprising about the results? Well, we have a long history of the impact of technological progress on labor market, right? And what we have learned from history is that technological progress is great. It increases productivity, it increases employment, and the way by which technology increases employment is by reallocation across occupations. Once that you have a technological advancement, there is some displacement effects, but then people add greater skills, invest in human capital, and employment increases because there is a change in the distribution of employment. And the way we try to understand this is with the so-called skill bias technological story. I mean, there are complementarities in some part of the job distribution, and we exploit those complementarities. What is new in the discussion about artificial intelligence is that people tend to think that artificial intelligence is going to displace jobs all over the employment distribution. So there are no complementarities, or not the big complementarities that we have in the past with the new technologies. So you are going to see displacement all over the distribution. Okay?
You didn't believe that.
Well, it's what people say. It's what people in the tech industry say. Okay? This is going to be very, very disruptive because everything could be automated. And yesterday, Daron and Anton were discussing about what is the time span for a human level artificial intelligence. Okay? So this is what the tech industry say. According to our results, maybe it's not surprising to you, it's not surprising to me either, this seems more like a skill bias technological progress so far, it seems more like a skill bias technological progress than, a general purpose technology disrupting all kinds of occupations and changing completely the need for human capital. Okay? So I remember Chris Pisarides was very recently in Madrid, and he was asked about the impact of artificial intelligence. So he seems to have this idea of a big disruption, because what he said is that we no longer need mathematicians, we no longer need statisticians, because everything is going to be done by artificial intelligence. Okay? This was his response. The other side of the debate is, well, given that artificial intelligence are going to do this task, we need mathematicians and statisticians precisely to understand what artificial intelligence is doing. Okay? So you have these two positions in the debate. You ask for my position, I tend to be more on the second than on the first. So on this, I will disagree with Chris. But okay, I think it's still too early to see whether the disruption effect of artificial intelligence are going to be so deep and so profound as some people are saying. Yeah. And that's why we took the approach that we took in this paper. We said, well, if there is something, so far, it has to be in the employment distribution. It has to be in the wage distribution. And we didn't find it.
We have 2 minutes, so I have a question maybe for both of you. So these are the papers are nice. They do quite similar exercises. One more on the descriptive side, the other more on the try to get causality. So probably it would be nice to have in both your papers, like this put some more weight on the description, and maybe you could talk each other to so coordinate about the the interpretations of different patterns. And it seems to me that there are big differences in Europe and United States. Maybe are related to the very different institutional settings. So and maybe of course this would be very much speculative, but we can take a luxury, maybe in a special issue for that really interests a broader audience to have some speculation about what is due to different trends, what is due to different institutions, and it would be quite nice. Maybe then we'd be Giacomo and Emilio more on the top of that, but to have some discussion on why we observe differences in and some just descriptive code, maybe some similar descriptive exercise on the side and the other. Then each of you take your own pattern, but some.
You allow me, it's not so much the differences on the results, but on the focus of the paper. The two paper focuses on two different things, which are relative, of course.
Of course, that's clear. But still the two things are very much related, quite different.
Can I add?
Okay, thanks. So, I take the opportunity to, so I really enjoyed the presentation of Juan. I like the paper. Initially, I was also thinking that, at first sight, there seems to be, the two messages seem to be a bit different, but now I'm more and more convinced that that's not necessarily the case. So if this measure of occupational exposure is mostly driven by complementarity, and if this is correlated with our measure of AI employment, then actually the two results are completely compatible. So AI employment goes up, overall employment goes down, so the AI employment share goes up. So, which again, I think it points towards the direction that we need to better understand what this AI exposure is really capturing. So I don't think there is, I think it's a good idea that the two papers talk to each other, but I don't think that there is a fundamental incompatibility in a sense in the results at all. And then, I was asked also what is surprising. It's a very important question. So the literature talks about these, so we are not adding something completely new. So the effects are there, they have already been discussed in the literature, but the theoretical prediction typically here is ambiguous. So we need empirical evidence and then there are two sides of the debate. If you ask Filippo Aghioni, he's very optimist about these things, about new technologies, so typically he always claims that employment effects are going to be positive. And Daron is on the other side, is much more negative. And indeed, in his book, in his papers, he's claiming all the time that without the right regulations and the right incentives, AI may well be used to power automation, to automate jobs. And this is much more in line with what we find. So our contribution is to try to settle this debate, not to add something completely new. And in terms of what is surprising, well, there was quite a bit, there was a lively discussion about our results. So it seems that many people found the negative effect surprising. As I said, it was not necessarily our prior, so we were a bit agnostic when we started this project. And as I said, it's open to some extent to interpretation. Probably the most, to me at least, the most convincing explanation for the finding is that local AI is indeed promoting local automation of employment. And I think this, is one of the possible reading and contribution of the paper.
Francesco, you want to add something? No,
Yeah, actually, I was just following on comparing the results on the two studies. I mean, the migration literature has already been mentioned, and it's a clear example that depending on how we slice the labor market, how we define the treatment, we get different results. But actually, in the two papers, because the pattern of IV and OLS results suggests there is this positive, there is this upward bias, and so there's this positive correlation between employment and adoption, which is what I guess Juan is showing, even if the exercise is slightly different. And so I guess the difference is in the OLS, because your OLS, Gino, are negative already. So it would be maybe interesting to explore more whether the negativity of your OLS is like robust, let's say, and because I mean, at least in the presentation, we mostly saw your two-stage least square results.
Yeah, so just a comment. When with Emilio we discussed about the papers, we were in fact noticing the difference between the papers, and it's great that today is actually the discussion is showing that there is there is a way to interpret these different results that somehow enriches our understanding of what's going on. So, in fact, I think we will ask you to talk each other metaphorically and probably more than that in order to have a deeper reflection of what happened today and what we discussed today in the papers. So, and by the way, thanks a lot for the presentation and presentations and the paper. I just have a small comment on the discussion and the point about the observation that so far what we see is a skill bias technological progress. In fact, so if you think, so it's really difficult nowadays to separate our view on AI that we currently have thanks to the developments of models, LLM models, that are going in the direction of general artificial intelligence. While this is pretty new, market applications, I remember when we started discussing with Emilio several years ago, market applications of AI in the past were not at all general. They were very specific. That's why, to some extent, is very much in line with these observations that sectors and specific sectors are much relevant. Then I have a small comment actually question to Juan. You mentioned at some point that labor market regulations matter a lot. There's not so much of that in the paper, so if you can elaborate a little bit on that, what you mean.
Well, it's basically the last table in the paper where we correlate the beta coefficient for the regression with indicator across countries of the degree of strictness of employment protection legislation and supply of human capital and so on. And my comment was basically about the positive correlation between the positive association in the regression and human capital and the negative correlation with employment protection legislation and the degree of competition in product market. So it seems that more rigid labor market, countries with more rigid labor market have a smaller association between artificial intelligence exposure and gains in employment share. But this is very tentative. This is just a way of providing food for thought for more studies on how the transmission of artificial intelligence depends on the structure of the labor market.
Okay, so thanks so much. We are a bit late, 5 minutes late, so we can adjourn in 10 minutes for the very last bite of the day. So Anton's presentation.
This here was the original title of the paper. Now, as I was revising it for the conference, I was thinking, and this is kind of a question I have for the editors. Sorry, this is flipping too quickly. How about the following title? Concentrating intelligence, scaling laws and market structure in generative AI, but we can discuss it afterwards. Because in some ways what I really want to focus on in this paper is the importance of scaling laws and the trajectory on which generative AI systems currently are. And what I will do is I first want to give a brief introduction. I will talk a little bit about the data describing the current state of generative AI and the market of generative AI. Then I will focus on what these scaling laws for artificial intelligence imply for market structure. And then I want to derive and distill some lessons of that for both antitrust policy and also regulatory policy in this space. So a brief introduction. Generative AI is based on a set of models that are called foundation models. These are large and deep neural networks that are trained using really significant amounts of compute and data. Compute is basically a new noun that people in the Bay Area use to summarize the total amount of computational resources going into training AI systems. And then what also makes these foundation models special is that they are literally foundations that can be adapted to many different downstream use cases. So for example, a system like GPT-4, it can be fine-tuned to be a chatbot, or it can be fine-tuned to be a customer service representative agent, or it can do many different things. And that's why they are called foundation models. The reason why I guess we are having this conversation is that there is a sense and an expectation that foundation models may have a very significant impact on the economy, and depending on whether we listen to Daron or to Goldman Sachs, they are expected to underpin a very large fraction, or maybe a smaller fraction, of cognitive work in the economy and of economic activity. So I thought last night I will include Daron's figure of 0.71% versus Goldman Sachs predicts that this will create 7 to 10% of economic activity within the decade. And that implies that the market structure is of great importance. It's supposed to be here on this slide. So who are the principal players? And one of the reasons I wanted to put up this slide is because I will come back to what that implies for the competitive dynamics. So there are essentially three top players right now: Anthropic, OpenAI, and Google DeepMind. I have ranked them by this measure here. It's called the MMLU score, which is essentially a benchmark massive multitask language understanding is what MMLU stands for, that measures how good these systems are. And there are basically three systems that are almost at the same level right now, and this has changed since I submitted the last version of the paper just 4 weeks ago. Anthropic is the first one, OpenAI second, Google DeepMind is, depending on how exactly you measure that score, on par with OpenAI. And the fourth one, which was essentially just dismembered by Microsoft, because Microsoft hired the two top executives that created Inflection AI, is no longer really in business. And then after that, there is a large number of systems that have, I would say, also similar capabilities, similar scores, but that cannot quite meet the capabilities of the top three players. Who are the principal players if we measure it by revenue? Well, you can see here at the top right and bottom segment, there's OpenAI and Microsoft. They are both using the same foundation model, GPT-4, and together hold about 69% of the market. Google has a small sliver. Amazon Web Services, which runs Anthropic, and Llama also have a small sliver, and then there's a whole bunch of others. But essentially, you can say 2/3 of the market as of last year belong to OpenAI's system. This is also reflected in the market valuation. OpenAI is currently valued at around $86 billion, Anthropic at 15, and after that, everybody else at much less. And finally, what we can see is that in all these leading players right now, there are actually large investments by the existing big tech companies. So OpenAI has a large, by some measures, majority investment from Microsoft. Anthropic, their closest competitor, has a big investment from Alphabet, from Amazon, but also others. Inflection AI no longer exists. Hugging Face, which is also one of the important players in the field, has big investments from all the big tech companies. And even Mistral in France has a big investment by Microsoft now. The reason I want to emphasize this is that all these models require a tremendous amount of computational resources, and the investments from, for example, Microsoft, Alphabet, and so on, are essentially in the form of providing them with computational resources. So all these small, if you want to call them that way, startups, essentially depend on the big server farms of Microsoft, Google, Amazon, and so on. And that gives the large technology companies really outsized influence over this market. If we look at the hardware side of the equation, the concentration in the market for GPUs, which are essentially the chips that you use to run cutting-edge language models or other generative AI systems, you can see that the market for chips is extremely concentrated. NVIDIA essentially owns that market. And then I want to just flag that antitrust authorities have recently started to pay attention to this market. So in the US, the FTC has started an inquiry into the competition dynamics and into the investments of big technology companies into the startups. In the UK, the Competition and Markets Authority has established guiding principles for the market for foundation models. And in the EU, Margrethe Vestager has made a statement just in January that the Commission is paying close attention to the competition dynamics in this market. So now I want to turn to the technological characteristics of these systems and what they imply for market structure. first, I want to focus on the cost structure. What does it take to develop a cutting-edge foundation model? And that essentially takes 3 steps. The first step is, by all measures, by far the most important one when it comes to costs, and that is the pre-training, which essentially creates the foundation. So one estimate is that Google's most advanced system, Gemini, costs $630 million to train, and 3/4 of that cost were essentially the pure cost of computational resources. So for us economists who occasionally run models, this is really quite stark. Imagine you press the run button on your computer when you run a model, and that's $630 million out the door. But that's what Google DeepMind did to train their Gemini models. Once you have this pre-trained foundation, you can fine-tune the model to specific applications, for example, to be a chatbot. And in that fine-tuning, there is an important role for application-specific data. So as we see these systems roll out more and more to specific industries, it may also be of growing importance that we need sector-specific proprietary data to make that happen. Right now, we haven't seen very much of that yet, so we can't say a lot about what that means in terms of antitrust concerns. And then the third step is, once we have fine-tuned the model, we have to use it to essentially create output. That's called inference, and that's the only variable cost of deploying foundation models. And by some measures, this inference step is actually incredibly cheap, certainly incredibly cheap compared to the creation of the foundation. For GPT-4, for example, it costs currently about 3 cents to generate 1,000 tokens. It means 1,000 syllables, or that's roughly 750 words in the English language. So if you compare that to how much it costs for a human to write 750 words, this is like a rounding error. This is almost free. And based on this really low cost of inference, you can say that in some ways, once you have trained one of these foundation models and fine-tuned it, producing output with them costs essentially nothing. So we had a discussion yesterday of the productivity effects of generative AI systems. My perspective is that once we have a system in place, producing a certain task essentially has a 90% or greater productivity gain compared to if a human performs that task, because this cost of inference, of running the model once it is produced, is so low. Now, what I want to focus on next are these so-called scaling laws. So if you look at what has driven the advances in generative AI, not just over the past 15 months, which is when the public has really paid attention to it, but over the past 15 years, you can see that there has been a regularity that the amount of training compute, the amount of computational resources deployed to develop the most cutting-edge systems has grown at a rate of 400%, grown at a rate of 300% every single year. So this is a logarithmic chart. You can see the total amount of floating point operations on the vertical axis. And the trend line here shows us that the training compute has quadrupled every year. And so if you look at, let's say, the top right, the most expensive system trained to date is Google's Gemini. That has cost about $630 million, or roughly $500 million for the pure compute cost. And if you listen to basically the business plans of the leading AI companies, OpenAI, DeepMind, Anthropic, they say, well, we plan on continuing this process of quadrupling the amount of computation for at least the next 3 to 5 years and possibly longer. So if we extrapolate just based on the regularities of the past, what would this imply for spending in the coming years? You can see here there is a confidence interval and a mainline prediction. The mainline prediction would be that by the end of the decade, we would spend $1 trillion on training these systems. And you know, Sam Altman, for example, recently was on record as trying to fundraise $7 trillion to develop more and more advanced AI systems. Now, why are they doing that? Well, the reason why they are scaling the compute is because of scaling laws that tell us how much better the AI systems become when we increase the compute inputs that we put into them. So specifically, over the past decade, people working on foundation models, and in particular large language models, but also image recognition systems, this is something that holds across basically the type of application. People have found that if you just increase the amount of parameters and data, and by extension the amount of computational power that goes into training these systems, you obtain predictable performance gains. And based on these scaling laws, they can predict, well, if we continue to quadruple the amount of computational resources going into these systems, they will be by this much better and then by that much and so on and so forth. So it makes for predictability. It allows OpenAI, DeepMind and so on to predict what will we get out of it if we sink $1 billion or 2 billion or 10 billion into our next systems. And OpenAI, for example, at this point has enough funding to continue this scaling for at least 2026. And if their predictions that these systems are really much more useful turn out to be true, I think it is plausible that we will continue those scaling laws for at least another 5 years. So if you look at these costs, that has important implications for where the market structure in these systems is going. And let me spend one more second on this slide. And in particular, you can see that having to spend this tremendous amount on developing one single model really creates a significant fixed cost that makes it difficult for the market to support a large number of players. So this scaling naturally leads to concentration. If we have a market with very significant fixed costs, it becomes difficult for that market to sustain a high level of competition. Now, and there are also concerns about vertical integration in the market for foundation models. On the upstream vertical integration, that would imply that foundation models integrate with the producers of compute. You can see this, for example, in the case of Google. Google produces its own computer chips. They are at this point not quite as efficient as NVIDIA, but they are using them. You can see this with NVIDIA, the main producer of computer chips. They invest heavily in AI labs, and they allocate their chips very strategically to make sure that they spread them across a large number of labs. And you can also see this with Amazon and Microsoft, which are both working on proprietary chips. a second source of inputs into foundation models are data providers, and there you can also see upstream vertical integration. So Google uses a lot of the data from its platforms, for example YouTube, to train its models. Meta is using data from its social networks to train its models. Twitter explicitly advertises, or I should say X explicitly advertises that their data is used to train Elon Musk's leading foundation model. So there's vertical integration with data providers as well. And then finally, we see an increasing amount of vertical integration downstreams in products. And both Google and Microsoft are integrating their generative AI offerings in a wide range of products. Of course, Microsoft has a history of essentially using vertical integration to foreclose markets, and that implies we should pay close attention to what is happening there. So now I want to turn to my interpretation of how I think about the antitrust concerns at present. I want to observe that right now, if I look at the level of competition in the market for foundation models, I see there is a fierce race among the top 3 companies producing frontier AI models. They do enjoy significant first mover advantages, but they are engaged in fierce competition. Perhaps something like a Bertrand model of competition is a good description of what they are doing. However, we can see that the rapidly rising costs of training these frontier models is reducing the number of players. Like, for example, what I mentioned before, the fact that Inflection AI was essentially dismembered by Microsoft happened because the CEO of the company essentially realized, well, we just can't sustain that pace of increasing investments in the face of stiff competition. If we look at models behind the frontier, there is what I want to call a competitive fringe. And in fact, I would argue competition in that competitive fringe has pushed the cost of models to zero. Companies like Meta or X by Elon Musk are open sourcing their models because I guess there's no other way of reducing the cost of your model than to just give it away and let people copy it. If we look at the market for chips, NVIDIA has this really strong monopoly status, but it has earned that status through largely legal means, I would say. If you look at their most recent income statement, they had a 76% gross margin, 56% net margin. So that means every dollar they receive, 56% are pure profit, right? And that tells us that is very close to a monopoly. So what are the antitrust implications of these findings? Well, first, and I think this is kind of common sense, we really need to be very careful in terms of oversight of mergers, of acquisitions, but also, and this is perhaps receiving less attention, oversight of exclusive contract deals, because increasingly, when the big technology companies are investing in the leading labs, this takes the form of exclusive contracts. You can only train your systems with our servers, and that makes some of the startups in this space strongly affiliated with existing big tech companies, and that almost looks like a quasi-acquisition in some respects. And yeah, so these exclusive contracts and the strategic investments that large technology companies are making in the startups producing generative AI need to be viewed very carefully. In the space of chips, one possible action that would address the highly concentrated structure in that market would be to separate the development of the chip software from the chip hardware design. So right now, leading companies like NVIDIA are doing both together, and the chip software, it's called CUDA in the case of NVIDIA, is in some ways very much a natural monopoly. Like, for example, the operating system of PCs is a natural monopoly. And by separating those, one could make the market a little bit more competitive. Now, if we have this strong tendency towards natural monopoly, that means competitive forces are blunted, and that means essentially consumer choice in all other respects won't function as well as it does in a competitive market. Normally in a competitive market we say we don't need to regulate aspects like reliability, accessibility and so on, because competition will take care of it. But in a highly concentrated market that's no longer true because competition is less. So as these foundation models become larger and larger and their influence on the economy rises, they may soon share more and more of the characteristics of utilities, in the sense that they underpin a large fraction of economic activity. A large fraction of the economy depends on supply of, let's say, language model services, just like all of us depend on the supply of electricity right now. And there are a bunch of regulatory measures that we suggest that should be taken in the context of such a market. First, we should ensure a level playing field between AI and non-AI providers. For example, liability frameworks should be technology neutral. If you offer medical advice right now, you are highly regulated if you are a doctor. And if you are a chatbot, you can just put a little disclaimer at the bottom: this may be subject to hallucination. So the question is that fair competition? A second issue to which we pay some attention is this question of data governance. Data governance can aid competition, but it can also strengthen monopolies. And in particular, rules like portability and interoperability can help to reduce market power because they make it easier to move from one competitor to another. But many data governance rules, in particular privacy regulations, actually restrict the movement of data and may help to entrench incumbents. So we need to be aware of that when we design privacy regulation. We don't want to do that in a way that it essentially entrenches incumbents. As these models become more and more integrated into the economy, we should also be concerned about the systemic risks that arise from that. If everybody uses one or a small number of foundation models to conduct their business, it means that we are all susceptible to the same vulnerabilities or attacks, or to the same potential errors. And that kind of homogenization reduces the robustness of our economic system. Another point that we focus on are the interactions between AI safety considerations and market structure. And this is something that can actually go into both directions. On the one hand, having a lot of competitive pressures, like what the top 3 companies are facing right now, it pressures them to push ahead and to develop the next model and release it quicker than their competitors, and that may actually undermine safety. On the other hand, having multiple players means that the resources going into the development of these systems are distributed across multiple companies. So if we had only one monopoly player, they would have a larger pool of resources, and they may develop bigger systems more quickly, giving rise to essentially greater capabilities and greater safety risks faster. So as we focus on competition concerns in this market, we need to pay very careful attention to how that affects AI safety. And then finally, as these systems become deployed more and more, and regulations increase, there will be large incentives for lobbying because the stakes are growing. So we also need to be aware of the risk of regulatory capture. And I guess that is one argument for why we may want to impose some of these regulations in a proactive manner, unlike what we did, for example, with social media companies, where it seems like we are in an equilibrium now, where it's almost impossible to impose tighter regulation at this point. So just to conclude, we are seeing this rapid progress in the scaling and advancement of generative AI systems and in the expansion of their economic impact. And that means that the market structure that we should expect tends more and more towards concentration. We argue that policymakers should proactively promote competition via antitrust measures, but also in tandem regulate systemic risks, safety issues, level the playing fields, and so on. And ultimately, the goal is to steer this transformative technology in a way that broadly benefits all, but also to remain responsive to the uncertain nature of the technological advances that we are seeing. So one perspective is that this scaling may continue for a very long time. Of course, it could also happen that we find out in 3 years we have reached the ceiling, and then we won't need to be as concerned about these systems being natural monopolies. Thank you.
Thank you so much, Anton. So now you are Doshien for the discussion.
I would like to thank the opportunity to discuss this interesting paper. Let me start by saying that I prepared a new second title. I'm an IO economist specialized in digital platforms. So I will try to be complementary to the presentation made by Anton. So overall, I think it's very comprehensive and up-to-date paper on the competitive landscape of the foundation models, and the paper provides a very timely, good snapshot. But I think there is trade-off between breadth and depth. For my taste, the paper is a bit too broad. I like the discussion of vertical integration. I think the paper can be enriched by incorporating what we learned from digital platforms, because in the recent years, worldwide, there have been so much discussion about how the market concentration in digital platforms, how we should regulate these platforms. And also, the second point is very optional, but Anton seemed to follow very well European regulations of AI and digital platforms. So I think I would push you to incorporate these materials at relevant place. And yeah. So some bottom lines of the paper is that there is huge market concentration in the inputs of foundation model, like compute, data, and cloud. That generates concerns about market concentration and entry barrier in foundation models. And also, you need to have access to these inputs. This may induce foundation model providers also have an incentive to vertically integrate or to sign exclusive deal, for instance, with cloud providers. I agree with these bottom lines, but I'm trying to be here complementary in the sense that this approach focusing on scaling low and inputs is very much in contrast to the approach taken by many recent policy reports. Someone say there are more than 100 policy reports on digital platforms. So here I just write 3 famous reports. So which they basically focus on the intrinsic characteristic of digital platform markets. And for me, foundation model is also a digital technology, maybe an extreme form of a digital technology. So 4 main characteristics of these platforms: strong economy of scale and scope. Here it's really extreme because, as Anton explained, the current consensus about the prevailing, the most efficient paradigm is that you use huge amount of computer data to train a foundation model, and then you fine tune it to adapt to all kinds of applications. So very, very large fixed cost, very small marginal cost, which can be applied to all variety of applications. So it's really an extreme form of economy of scale and scope. Sorry, it's not going to the direction I want to have. Okay. And then the second characteristic of this platform is network effects and lack of multi-homing. And third, data is critical input and data feedback loop. So I think the first 3 characteristics apply very well to foundation model. And people think that these are forces of market tipping. Okay? So intrinsic characteristic already point to the direction of a market tipping. And I think one referee proposed to make a comparison between search and foundational model. I think this might be useful. Personally, I think if there is similarity between search and foundational model, I think it's data-driven network effects. There are some empirical papers in the area of search. But the difference is generative AI is general purpose technology with much, much broader impact on economy. And also, the ecosystems of generative AI are starting to build. For instance, in the case of OpenAI, you have these almost 1,000 plugins and millions of GPTs, which generates indirect network effects. And in the case of customized service for business users, because they are going to use their own data to fine-tune the model. So that may generate very large switching costs. So I think that it is going to be useful to provide a full description of ecosystem, like focusing on OpenAI ecosystem, and discuss network effects, switching costs, and data feedback loop. All of this generate first mover advantage. And so there are, this is very optional, but since you seem to follow very well European legislation, and so you may also talk about them and discuss them. I think it's useful. For instance, DMA article about data sharing in search engine can be discussed. Because this is a measure, ex post measure adopted after the tipping occurred in the market. But it would be better to take some ex ante measures regarding data, to reduce the probability of a tipping. And also, European AI Act has several articles about general purpose AIs with systemic risks. You may talk about them and discuss whether they are enough to, there are enough measures against systemic risks. And finally, also Digital Service Act has articles on very large platforms also with a systemic risk. So in particular, this article is very interesting because it allows data access to vetted researchers for the purpose of conducting research that contributes to the identification and understanding of systemic risks. So, and in particular, I think competition authorities are very interested in the relationship between cloud computing business and foundational models. So I would like also invite you to be a bit different here, dependency of a foundational model on cloud service at various stages of production, like pre-training and fine-tuning, inference. One worry is that this hype about the foundation model may help the big three, Amazon, Microsoft, and Google cloud incumbents to further consolidate their market power. How, and then what can be done about it? I think it can be useful. For instance, in a European context, maybe a government may have incentives to build a supercomputer to provide domestic AI companies to relax the constraint on the compute. But this may solve a problem at the free training or fine-tuning stage. But still, at the inference level, if they have to rely on big three American cloud companies, still there will be some serious dependency. And I don't know whether this is what's happening with in the agreement between Mistral of France and Microsoft. And also, we need to take a perspective of a country who is not US. Okay. Then there is issue of national sovereignty and competition between American foundational models and domestic one. Because like AI, military application of AI, for instance, this is very, very important. And also health application or some public sector application, all these have a very, very sensitive data. And so you do not want to use American models for national sovereignty reasons. But then there is issue of how to create a level playing field, because there is a huge economies of scale and scope that benefit American models. By the way, there is think tank called Labour for the Long Term in UK, which argues that £1 billion promised by the government is not enough to protect the future independence of Great Britain. They say Labour should pledge £11 to build Brit GPT AI. And here is my personal stake. Still, you can, even though you introduce more competition, may not be enough, because we know that in the area of AI about existential risk, there is a whole spectrum of opinions, divergent opinions, even among researchers working on AI. And there is a kind of adverse selection in the sense of who is going to work for commercial AI. It's those who believe that AI does not generate existential risk. Okay, so even though you foster competition, I think there can be a problem. So I'm concerned about this imbalance between academic research and commercial research in foundational model. As you know that AI PhD is going to industry has increased dramatically from 21% to 30%. Why you go to industry? Because they not only they pay more, but you benefit from computing power and access to proprietary data. But commercial research agenda is biased because they do not take into account much societal implications of AI. But on the other side, academics, they just do not have access to compute. They are prevented from developing cutting-edge models, and they are not even able to check the work of industrial researchers. So in US, the federal agencies like NSF launched this National AI Research Resource Pilot, which basically provide access to compute and data to researchers in academia. I think something similar should be done in Europe. And so there are a few minor comments. Do I have 1 minute? Or, yeah. So like when you say that about this exclusive deal between OpenAI and Microsoft, I think you should, it would be useful to specify exactly what is the concern. Is it the concern is because of a kind of bundling between access to cloud compute for free training and also for inference, such that all business customers who want to use the OpenAI model, they should go through Microsoft cloud service. And so also when you talk about methods using open source model, you could also explain why, what motivates, what kind of gains Meta expect by doing that. And I have a lot to say about the chip industry, which is really, really important. But even IO economists, I don't think they pay much attention to what is the source of market power of NVIDIA. And you don't say about TSMC, what is the market, the source of market power, monopoly power of NVIDIA. But NVIDIA here sponsors like an entrant cloud computing company with its own chips. So that particular action actually promotes, makes the cloud market more competitive. So overall, the paper provides comprehensive, up-to-date snapshot of the competition landscape of foundational models, and access to data and compute and cloud may generate entry barriers and create tendency for vertical integration. But I think it would be useful, also to describe the main intrinsic characteristics of the foundational models, like the digital platforms, and point out the tendency of tipping. And I'm personally very concerned that there is a serious risk from AI's trajectory in the coming 5 to 10 years, largely determined by decision of just a few American commercial business. while this technology has a huge impact on the whole economy, world economy, and also, I mean, the mankind. Thank you very much.
So much. So, Anton, unless you want to respond to some points, since we are a bit late, I propose to have a round to collect questions, and then, yeah.
Let's do that, and let me just say first, thank you very much for a really insightful discussion. And I will respond to a few specific things after.
Exactly, so we try to wrap up everything. So is there any question? Otherwise, I have one broad comment question. So, I mean, we're a bit discussing this with Isabel. I think this is really so the example of where, let's say, traditional antitrust should have an eye related to, let's say, political economy, right? So sort of, it looks like the problems of brand Asian antitrust that kick back on a much larger scale than what we have seen in the past for any other industry, right? So much more than electricity and others, because we are at the global level, right? So that's something that maybe you have a take on that. But yeah, there are all the elements of going back and forth between potential enormous political influence on these kind of firms that could generate really dangerous circles. So in a very different setting, Luigi Zingales talked about the Medici's vicious circle of politics and market concentration in the past. Here, I think it's something at the nth power that may happen. Is there anybody else that wants to add something? No? Papa, no, sorry, you can just call me with this thing.
No, just a very small point. So I enjoyed a lot the presentation and the discussion. I found it very interesting, and I just wanted to second on this idea that it's a great opportunity also to discuss this question in the perspective of the European market and the EU existing regulation. And I think it's especially important given the scope of economic policy. So that would be really something great to I don't know, develop as much as you can for the next version of the paper. Thanks very much.
Please, just to mention that we like this paper very much because, well, it's an unusual paper, right, for economic policy. It's a very speculative paper, which is trying to present the competitive landscape in a nascent industry. And there is scope for policy in the sense that the idea is if we learn from the past that maybe there is scope for acting early on to avoid dominance, okay, in these very important markets, say 10 years from now, like what we had with platforms, like with big tech. And so we thought that this is a debate that we should have right now, and it's not sufficiently developed, and this could be a platform to kind of have more of these valuable yeah, so that was kind of what we liked about the paper. And I guess the struggle a little bit, and it's getting better with the revision and everything, is that it's comprehensive. That's good and bad in the sense that at the end of the day, you really want to know what is, given a conduct, why should we expect this particular conduct to be more prevalent in this industry relative to others? So the idea is to really kind of tease out what are the specificities of these industries that would make it, or that would make some conducts more likely to occur. And yeah, and of course, I mean, the kind of vibe of the paper is in a way negative. It's basically saying that we're heading in the wrong direction, which I think as a broad message is right. But it's also true that unfettered competition is also very risky, right? In the sense that what we have seen, what we witnessed in the past 2-3 years with foundation models is that OpenAI unleashed a model, and then despite all the legal departments of the other big tech companies advising against the release, there's been a rush, right, to release these models in the wild without proper testing, without any due diligence, nothing. So I guess this is clearly an example of too much competition, if you want, and so that in a way the idea is that this, improving the competitive landscape should go hand to hand with also developing the right guardrails, as they call them, to avoid that competition actually worsens the outcome.
Yeah, both a question to Anton and to Doshin. You talked about this level playing field, right, in this nice example with the doctor and the hallucination. And I'm wondering, I see the argument why you want to make sure that in some sense, these large language models, for example, are held to the same standard as what you would expect from a doctor, from a physical doctor. But isn't it kind of, wouldn't we risk that we really take away all the advantages that these kind of models have? I mean, maybe the advantage of these large language models is that they scale really nicely, right? You talked about the marginal costs. They can give a lot of medical advice to a lot of people very cheaply. But maybe it's very hard to get rid of these hallucinations, right? That seems to be the case, that in 1% of cases they start giving completely nonsense advice that can be dangerous. Is this really a best strategy to try to prevent this with regulation, which might turn out to be basically impossible for firms to be held up to that standard, to not have hallucination? Or is it that just consumers need to learn that the way they have to interact with AI is different than from a normal doctor, and that you shouldn't follow everything, that there's sort of this 1% of risk? And then to Doshin, your argument, you said that it's kind of potentially dangerous that a very small number of US companies are basically calling the shot in this industry. But I'm kind of wondering what's the alternative, right? I mean, the alternative is probably not that European companies are calling the shot, like in everything related to software. Europe has never been very strong. To me, the alternative is that maybe countries like China or Russia are really leading in this. And to me, that sounds much, much more dangerous, right, from the perspective from a European perspective. And so to me, it sounds, that companies like Microsoft or Google are doing this. Sure, we're worried about from a monopoly point of view, but in terms of sovereignty, in terms of being worried that we don't have these companies in-house in Europe or in Britain, it doesn't sound so concerning to me, given what the alternatives might be. Thanks.
Thanks a lot, Anton, for the presentation of the paper. Thank you, Doshin, for this very useful and interesting comment. I just have 3 quick comments. One is on labor market. I think it would be great if you could dig a little bit more in the paper about the implication. Well, the structure of the labor market, as Doshin was mentioning, is to some extent peculiar. To some other extent is not, because you think, for example, the drug companies, and they are attracting top scholars and somehow depleting the ability of public or in general universities to develop research. So there are similarities, but I think it would be interesting and important that you dig a little bit on that. I think it's also important that you relate the paper and the claims that there are in the paper to what has been the discussions in these 2 days, because there were some elements that are clearly important from what you said and vice versa. And so a stark observation to me is we're talking about investment in terms of trillions at this point, and for potentially tiny impacts from the macro perspective, 0.71%. So how can we square disincentives to invest in something that may have so tiny and small impact. So there may be a misunderstanding from some part or the other. So I think it's important that that's an example. I think there are other elements that emerged in these 2 days that may be relevant for you. And then I think you should dig a little bit more into what is the alternative. So I think we generally agree that the cost structure of these models will generate concentration, vertical integration, but then what is the alternative? So with digital markets, we thought we could rely on antitrust, which didn't work at all. We discovered, and so some countries started to regulate. So European approach was we need a regulation. And so I think it would be important we know that your paper is a speculative paper, so we are pushing you probably too much into too many directions, but I think we have an opportunity at this point. But in any case, thank you.
No, it's super interesting, and I know why your question, why there is such an investment with a tiny impact. So probably, Anton, you can answer this, but the impression is maybe first they listen more to Goldman Sachs and McKinsey than to ExxonMobil. It may be the case, or there may be a sort of ball here, which is going to be natural. But again, from a political economy perspective, which is mine, I think these kind of investments and the question we're asking, how different are from the past, how this is really different from the past, I'm going to give to these guys an enormous threat power vis-a-vis governments globally very soon, and that's an enormous economic value. Or beyond, Miguel. We have to wrap up.
Following up on that, just a quick thing that maybe they're investing a lot, and that's not going. And as Emoglu is right, that's not going to have a big impact on GDP because they're going to reap all the rewards. So it might be a zero-sum game that they're going to benefit a lot, and someone else is going to lose. So maybe it's compatible with that.
Wrap up everything. Thank you.
Yes, there are so many interesting and helpful comments that I think I can't do justice to every one of them. Let me take a kind of big picture perspective. When we started working on this paper, the point that you, Roberto, made, and that I think I kind of could hear from a number of you, that we should be concerned that if this technology continues, these companies will absorb a tremendous amount of power, both politically and economically. That was one of our driving forces, actually, in analyzing this. And the interesting thing is, if we look at the market, let's say right now, and if we were to freeze this, this is a market that's a couple $2 billion, which is nothing compared to the overall world economy, then it would be a really unimportant market. So as Emilio observed, we kind of need to speculate a little bit where this might be going, and if the predictions that this is going to be big are right, then the implications of everything that we are discussing here may be really important. And so that's essentially what the paper is about. But let's say I would still put some non-zero weight on the possibility that as Miguel observed, well, maybe this is all a gigantic bubble, and maybe we'll find out in 3 years from now that there isn't actually that much to be concerned about. It's not my mainline scenario. And I think as economists, our job is to some extent to apply risk-neutral probabilities to these possibilities. And the risk-neutral probability would be a little bit higher than the natural probability, because the implications of this would just be so important from a social welfare perspective. So there were a whole range of really interesting comments. Let me perhaps focus just on one in a little more detail, which is the European dimension of this question which both Doshin and Isabel and a number of others brought up. If we look purely at the productivity effects of this technology, and we are not concerned with national power and so on, then I think it is of no concern that we have, let's say, 2.5 big US companies supplying essentially the world market with this technology. Everybody can use GPT-4 and Claude and Gemini, and it would be a wasteful duplication of effort to develop additional competing models that would probably be smaller and less powerful in every single European country. But of course, we can't completely take out the national power question from the equation. At the same time, I'm concerned that US companies do have such a significant first mover advantage that it will be quite difficult to overcome that. And that leaves me in a little bit of a bind in terms of what I would advocate or not. I'm concerned that if we say, all right, Europe should invest 10 billion in a big European-wide, let's say, compute bank that can be used for research or for training maybe one single European AI model, that it may not go that well and that may be ultimately a waste of resources. In another world, could it be like a CERN at some point? Like CERN, where everybody in the world pooled resources to create one gigantic particle accelerator. In some sense, maybe that would be the best possible outcome. And especially if something like that would find buy-in from the Americans, then it could be the way to go once we reach like $100 billion models or something like that. I just have concerns that it may not work very well. And I will also say the National AI Resource in the in the US that was created by the NSF has actually not really delivered a lot of tangible benefits yet. It's been established more than a year ago, and that kind of shows us that it seems that the private sector and the force of competition, the technological race that we see there, seems to play a really important role in that type of innovation, and it's very difficult to square that with all the safety concerns and power concerns that we have all expressed in this session here. And I will follow up with a number of you individually on the specific comments over lunch.
So thanks so much, Anton, and thanks to everybody. So it's been a very, very nice panel. Okay, so it's a bittersweet farewell or arrivederci to most of you. Okay, and let me also thank Isabel, because it's been great to work with you on economic policy for the last 3 years. We had a lot of fun. So, but we're going to see each other on Monday because our offices are next to each other. But it's been very nice actually. So. My pleasure.